Ladies and gentlemen, a very good evening to all of you, and I would like to welcome you all for an insightful session on charging infrastructure innovations. I am Patum, your host for the day, and I warmly welcome you to the second webinar of the Battery Technology and Charging Infrastructure for Electric Vehicles workshop series organized by IEEE Y2N Pro. To give a brief overview of this workshop series, this is a comprehensive course that offers both theoretical and practical insights into battery technologies and charging infrastructures of EVs. This series addresses the surging demand for expertise in the EV sector, focusing on battery systems and charging infrastructure. You will be able to explore the evolution, operational principles, and future advancements of EVs, delving into battery technologies and innovations aimed at enhancing efficiency and safety. Getting back on to today's workshop, it will be on the area of ultra-fast charging technologies and wireless charging. Before moving on, we have some important announcements to make. We have already shared these guidelines to be followed during the workshop series. However, I will read the guidelines and make sure that you follow them for a smooth session. A quiz would be administered at the end of the workshop series on October 5th, where you would be assessed on the knowledge gained. The IEEE credential certificate will be awarded only if you achieve at least 80% on the above mentioned quiz and attend at least 80% of the sessions. Attendance will be marked at 3 given instances of the session. Therefore, please be present throughout the session. The recording of the webinar will be uploaded to the Google Classroom. And please rename yourself using the registration number provided in the handbook and your name if you haven't done so already. Today, we are honored to have a distinguished industry expert with us who will guide you through charging infrastructure innovations. Thank you, sir, for accepting our invitation and joining us today to deliver the keynote speech. Mr. Kasun Jayalath is a senior electronics engineer with extensive experience in embedded systems, Linux, and industrial automation. Currently, working at Vega Innovations, he has been instrumental in developing and maintaining embedded Linux systems for EV charging networks, demonstrating proficiency in middleware development, network control integration, and RTA methodologies. Mr. Jayalath's career includes roles as research and development engineer at Sri Lanka Telecom, automation engineer at Mars Holdings, and a graduate research assistant at University of Albany, Sunny. His academic background features a master's degree in electronics and automation from the University of Moratuwa and a bachelor's degree in electrical and electronics engineering from the University of Peradeniya. Mr. Jayalath is a dedicated professional who continues to contribute to technological advancements in embedded systems and industrial automation. So, ladies and gentlemen, please welcome Mr. Kasun Jayalath to deliver the keynote speech on charging infrastructure, innovations focusing on ultra-fast charging technologies and wireless charging. The spotlight is yours, sir.
All right, thank you. I'm going to share my slides if it is possible. All right, hope my slides are visible and I'm audible and visible enough for you. Can someone please confirm?
Yes, sir, you're audible and visible.
Right. So good evening, everyone, every students and organizers, and I should first thank you all for inviting me to this opportunity and letting people know, letting all the students who are studying or in professional careers know what are the key areas in this charging infrastructure and innovation, and how this EV industry are going forward in Sri Lanka, basically. And so I have seen in your agenda that you have been passed some basic sort of uh, lectures on battery technologies and electric vehicles. So I think that you have the understanding of what are the electric vehicles and what are the battery technologies used in electric vehicles. So next up is to understand how those electric vehicles and those how those batteries get charged and uh, make them move. So that is what we are going to focus on today. So not giving much sort of information and the technologies on ultra fast charging and wireless. So I will be focusing on uh, basically how we build the infrastructure, and starting from the slow chargers, then fast chargers, and finally I will be focusing on the ultra fast charging and wireless charging as well. So I'm Kasun Jayalath. So as the introducer mentioned, I'm a senior electronics engineer in ChargeNet attached to Vega Innovations. So we have a range of vehicles starting from we develop vehicles starting from scooters to uh, supercars. So there we sometimes you might not have seen the all the like the big fleet of vehicles we developed and we use, but in our day-to-day activities in our organization, we use them like quite often. Like we don't use any other vehicles for transportation. We have a sort of agricultural farm in Kandy, so a hill country. So where we used to go and back and forth from Colombo to Kandy like 2 times a week. So in a roster basis, we send our three-wheeler, one of or two of our three-wheelers 2 times a week to Kandy. So in that time in those to accommodate that mobility, we use our charging infrastructure. So and sometimes so those without our charging infrastructure, it is not possible to move these vehicles around at that intensive routine. So so the range and all the challenges of the road and all the elevations, everything should be considered uh, when we are bringing EV to the market, EV to the general public. Uh, so that is not possible without building a proper charging infrastructure around our country and around like covering all the places. As for example, to bring our three-wheeler from Colombo to Kandy, we need another. So we need a charging point. We needed a charging point in the middle because it basically consume around like 60% of its battery when it is climbing from Colombo to Kego. So we were in a requirement to build a charging infrastructure in the Kego, but it should not be a slow charger. So we have several chargers from Colombo to Kandy in that road, but we were in a need of a fast charger because uh, because we cannot wait, our three-wheeler cannot wait around two or a couple of hours just staying there until our three-wheeler get charged. So because of that, we built a fast charging station in Kego. So it seemed lastly we can do our routine work. So the three-wheeler go to the Kegol's fast charging station and it gets charged, and then it sent to Kandy. So it is actually in a very hill area in the Kandy. So it consumes a lot of battery power there as well. So when it is coming back, So it can fast charge within like 20 or 30 minutes from that Kegol charging station, and then it can come back to Colombo. So without going into any slides, I'm just just telling you the requirement of charging stations. Moreover, fast charging stations around the country to move the people here and there. Just a introduction. And so coming back to the lecture, so today I'm planning to go through these areas. First, I will do a little bit of introduction of how EV charging, what is EV charging, and then I'll go into the purpose of the EV chargers. So first, we need to understand what are the purpose of EV chargers, and then I have dedicated like 1 or 2 slides to understand some of the technical jargons and some of the basic terminologies that used in EV charging industry as well as in EVs. And then I move to how the EV charging station is formed, a basic overview of the boundary line of how EV charging station actually operates, right? And then in the fifth section, I will cover about L2 chargers, level 2 chargers, level 3 chargers, which is DC fast charging and ultra fast charging. As in the last section, I will cover up the future EV charging technology. So like mainly the wireless charging. So it is in my discussion. So there you can so for the basic introduction of EV charging, so everyone agrees that it is a decade of EVs because the battery technologies were are in advance, like so starting from the combustion engines, we have spent like 20 or 30 years without any other mode of technology. So those combustion engines have developed in 80s, and then it comes to a point where we need another mode of transportation because this combustion engines and burning fuel is not be sustainable in the future. So because of that, so the demand is very clear for EVs because we are running out of resource of fuel. So you can see in the second image, there is the image shows the energy market predictions from a research done by Norway. So in that research, it shows in the brown line you can see. Oh, there is a maximum demand which is predicted in 2030. So the demand for fuel, the oil, will hit into a peak when it is to 2030. So we are now in 2024. So it is just 6 years where the peak for oil will hit, right? So then we need to find an alternative method, which is electricity, which is booming in that period, starting from 2018. You can see starting from 2018. So it was growing up, and it is predicted that people more switch to the energy, the electricity energy for their vehicles. And also it is backed from the worldwide EV sales data, which is in the first figure. You can see this is the sales of EVs from 2014 to 2024. You can see it is exponentially growing in all the markets in China, Europe, and United States. And all the manufacturers are there. Like the manufacturers are also increasing. The first, like in 2008, when the Tesla get their like commercialized vehicle, Tesla Roadster. and after that, there was not much sort of manufacturers, but you have seen last couple of months, you can see how BYD and all the vehicle manufacturers make their EV departments, like they make EV vehicles, all the Mercedes, Porsche, Mustang, you name it, they make their EVs. And they have seen the future is there and they're moving into that. So there will be more resources like hydrogen vehicles, battery swapping technologies in the future. But in the near future, the EV will dominate the market. So that is the prediction. And the battery prices is also reducing. The battery technologies is as well as the battery technologies get advanced. So now, right now, there are vehicles that there are battery packs, vehicles that can go up to a range of 400 kilometers per single charge. So that is sort of enough for a consumer, for a daily commuter. That range for a single charge is enough. So the battery technologies have come to a place where there's no more like bottleneck in battery technology. So the bottleneck will be in the charging infrastructure and how fast you can charge the vehicle. So let's say you are going in a big journey and you suddenly consume all your battery power. And then what you have to do is you have to park the vehicle in a charging station, definitely, and get your vehicle charged. So actually, right now, even using very ultra fast technologies, it will take around like 20 to 30 minutes, not in ultra fast, but in DC fast charging, it will take at least 30 minutes to get your vehicle charged from 10% to like 70%. So that is sort of the bottleneck. So and that makes that industry, that makes that sort of domain uh, in like innovation happens where the problem is uh, stays, right? So that is the sort of demand of the electric vehicle charging. And for the in a Sri Lankan context, so we are not so far away from the adaptation for the electric vehicles. So we have seen so I've done a brief sort of research on the context in our country. So the first Nissan Leaf has registered in 2004. One of a brave guy who have decided to buy a electric vehicle, and he's going to charge his vehicle from his home electricity. So he might have some very tough time where in 2020, 2004, we don't have any infrastructure. So like those times are we have, Sri Lanka is not in a good form as well. And and we don't have any charging points and charging locations even in Colombo. Uh, so there were no EV policies, tax policies in 2000 and from like 2004 to 2000 and until 2018. And there were no any policy or bringing the vehicles. So all the vehicles treated as same like common vehicles in that time. And then it happens like 2016, the Paris Agreement. So we signed for that Paris Agreement, and that agreement were focusing on more sustainable energy, and it suggested to bring out some strategic frameworks for EV promotion and planning for the future demand and what are the issues. And they are convinced that the country need to have um, sort of a body or policy that regulates the batteries, the charging infrastructures, and the vehicles, and how the disposal should happen. Likewise, so like from that agreement, there was an overall EV policy framework which was starting to form in July 2023 by Public Utility Commission. So right now uh, they are making a regulatory framework for the electric vehicles and for the charging stations. So in the near future, all the charging stations in our country will be more regulated, and the more demand the places where we need to put the places charges will be advertised, and where people will pick, and likewise. So the ChargeNet was started in 2015. So we have our first charging infrastructure we have built in the same place we are in now, the Trace Expert City in Maradana. So right now we have around like 300 charging points around the country. We have a couple of them in Japan as well right now. So we were in the pioneers from 2015 to build our infrastructure around the country so that EVs are welcome to Sri Lanka. And we have gained a very large uh, uh, like the uh, response from people who are using our charging infrastructure for to make their vehicle move and get their vehicle charged. So 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 that is now context, right? So moving to the next slide, you can see first we are going to talk in this slide. We are going to talk about what is the purpose of a EV charger. So without having a purpose for something, it is not worthwhile. So in the cartoon, you can see how it is uh, showing how the electric vehicle manufacturers and the energy market uh, goes, and how the government in particular country try to bridge that gap, because the energy market is mainly the energy which is using from electric vehicles or the electrical energy. So we have, every country has a national grid, and their outlets as well. And EV vehicle manufacturers made their vehicles from batteries that needed, like that has uh, uh, different voltage architectures. And the government or the commercial charging vendors should bridge that gap properly. Otherwise, there will be these sort of problems might happen, because sometimes there will be incompatible charging stations, there will be incompatible vehicles to the network. So the ultimately the customer or the people or the person who bought this vehicle get stuck because they can't charge their vehicles. We even in our country we have seen several vehicles manufacturers and several occasions where someone modified their vehicle, or they have brought down a vehicle that which is not very much supported to our grid and network. So the main idea is the main requirement is to connect that grid to our national grid, and also the chargers that is connected to the grid should have proper circuitry to prevent conditions such as overloading, electric surge, and the communication faults between vehicle and the charging equipment. And sometimes there are contactors which is welded because of overheating. So those sort of protections should have in a charger. So it is one of a main purpose of connecting your vehicle to charge. Otherwise, you can charge your vehicle at home, but the home electricity or the power does not support much. So even the vehicle, so the problem happens when the vehicle can draw a lot of power from the network, but if you are plugging into your home, so it is not going to work until so your vehicle will not charge even though it is connected like 6 or 7 hours. So if you want to get your vehicle charged fast, so you need to connect to a proper charger. So the charger should have all these protections. And also we need to the charger manufacturer need to consider about the not doing any harm to the battery of the electric vehicle, because sometimes when it is not a proper standard uh, a charging point, so your vehicle battery get damaged because of these faults. So we have seen like a lot of scenarios where some Chinese manufacturers made their chargers and they don't have proper support as well. So the vehicle's battery sometimes damaged because of that. And the charging manufacturer also should count the to measure the delivered energy, because the everything is at cost. So it is cheaper compared to gasoline and all the fuel, but there is some cost. So the energy need to be measured precisely, and that amount should charge from the customer. And the payment collection, all that backend support should be there. And also to cover all the things, the charging manufacturer should adhere to the government and manufacturer guidelines and standards in charging standards. So I will talk about standards in the next couple of slides. So you will have a proper understanding on that as well. So then let's look at some of the technical terms which you will be seeing in my slides, and as well as in this sort of domain. So the first and foremost thing is the EVSE. So EVSE and EVCS. EVSE is electric vehicle service equipment. So all the wall mounted or the floor mounted, all the chargers and all this charging equipment is fall under this sort of term, EVSE. And EVCS is electric vehicle charging centers. So like if you have put up a couple of chargers into one location, and if you manage that operation, that location, so it is called EVCS, right? And then there are charging levels, L1, L2, L and L3. So level 1, level 2, and level 3 charges. I will be discussing about in the next slides. So those are different charging levels based on the power that it can deliver to the customer, to the user. And then you can see some foreign terms like CHAdeMO, CCS, GBT, and Tesla charges, type 1, type 2. So what are those? What are those? Those are the connector standards made from vehicle manufacturers. So the CHAdeMO is the Japanese standards, and CCS and GBT are the European standards, and Tesla, we know about the Tesla. So they are different standard and charging infrastructure as well. And the CHAdeMO is like charge the move. So it is sort of a Japanese standard. So Nissan Leaf and other Japanese vehicles have this sort of connector. So it is a connector standards, right? So then we have some regulatory frameworks which has developed some uh, uh, comprehensive standards such as ICE 61851 and J1772. So those are the standards that ensure the safety and interoperability of those chargers, because the chargers should not focus on one vehicle type, right? So every vehicle type should come and easily get their vehicle charged. So because of that, so so every charging manufacturer should make their charges based on these standards. Otherwise, the vehicle the battery management system will not allow the vehicle to charge. And the last sort of term I'm listing now is CPO and ESP. So the CPO is charging point operator. So it is seems like ChargeNet and all the sort of operators who are in this domain. And ESP is the electricity service providers. So right now we are LECO and CEB. So they are the people who provide the electricity, the ESP, and CPO is the charging point operator. So here in this slide, I have list down just to see. So what are the standards? So what are the standards that should comply if any one of you try to build a charger? Because those standards are there, so you can get them from them, and you can study those standards thoroughly to build a charger. right? So you can see, so we have talked about IECE 61851. So it is in the middle. Uh, so it is in here. So it is, so you can see one. So it is in here. So it is covering various charging modes, communication protocol, and safety features. So it is very crucial because there is a communication protocols that that communicate back and forth with the for the vehicle. Give me a minute. Yeah. And this standard SAEJ 1772. So they are focusing on the requirement for electrical connectors and communication protocols for level 1 to charging in that region. So likewise, these standards focus on different areas uh, of electric vehicle charging. So better to refer them before study. Like if you want to give a like have a comprehensive understanding of how these actually works, actually communicate with the vehicle, you can read all the manuals. So that is these are essential. And then this is one of our informative slides that I will be spending a couple of minutes. So here it is, yeah, see the title. Yeah. All right. So this is how the vehicle charging station formed actually. So in my let's focus on the diagram in my left in your left side. So you can see the grid connection is there, and the green boundary is boundary line the charging station. So in there we have two basic chargers you can see in a charging station. The first type of chargers are slow chargers, and the other type of chargers are fast chargers. And in a purple color boundary, you can see the electric vehicle. So if you have like in the previous lectures, you might have covered that electric vehicles has a battery, of course, and it has an onboard charger that allows AC current to connect to the vehicle. So on the onboard charger convert, it is a rectifier that convert AC to DC. And if you are using fast chargers, so the battery will be directly, battery terminals will be directly connect to the terminals in the charging station. Positives and negatives will be directly connected. So, it is very crucial that fast chargers should follow the proper standards so that because you are directly connecting your charger um, uh, to the vehicle, to the vehicle directly to the battery. So if there is any problem, your vehicle will get your vehicle battery will get damaged. So in the slow chargers, so there are two sort of sectors, L1 and L2. So L1 is basically the home charging. So like it is sort of a just adapter, the 12 ampere adapter or 13 ampere adapter that you can charge your vehicle with. So even in your home, in normal, the vehicle manufacturers give their charging equipment. So it is basically the L1 charges where we have 12 ampere output. And L2 charges in the other case is the 30 ampere outlet. So it comes in 3 pairs and 2 pairs, single pairs as well. So these two, L1 and L2, are known as slow chargers. And in the other hand, the fast chargers are called L3, the level 3 chargers. So there we convert the AC to DC. So we have power modules that convert the AC current to DC in several steps. So in next slide, in the coming slides, I will briefly go through what are the stages and how it all like combined, right? So AC to DC, and so first it converts AC to DC, and then it regulates its current. In DC to DC, it like regulates its current. I put the multiply sign in because it is showing the power modules. So we have like power modules for like 30 kilowatt power modules, likewise. So if you want to if you want to build a charger which has 90 kilowatts, you can use three such modules, right? So that is why there is multiply of n. So you can put n power modules and combine it together and give final power output to the battery. So in the fast chargers, always like it is like 100 amperes or more current will be delivered directly to the battery. So in my right hand side, you can see the different ports. So in the previous slide, I was talking about CHAdeMO, CCS, CCS2, and GBT and Tesla. You can see those are the ports that is available in the world for the electric vehicles. So so there are two types like AC and DC. So AC is always about slow charging, and DC is always about fast charging. So in DC column in the CHAdeMO, right now, as I have shown in the previous slide, so the CHAdeMO connectors is come with Nissan Leaf, Mitsubishi Outlander, such vehicles. So they comes with that charging port. And so normally a vehicle has two types of charging ports, like the AC and DC. So either they can in home they can charge their vehicle using AC, which is in slow charge, and in the middle of some journey or some trip, you can plug to a fast charge and charge your vehicle much faster. So in Japan, the connector standards are Type 1 and CHAdeMO. And for the North America region, we are the Ford Mustang, BMW, Chevrolet, and all these vehicles have CCS ports and Type 1 ports for AC and DC. And for the Europe, they have Tesla Model S, BMW, and Volkswagen, Audi, Tron, and all these German brands comes with Type 2 charger for AC slow charge and CCS2 charger for DC fast charging. And in China, they have two sort of chargings like GBT for AC and the same as for GBT for DC. So it is a bit different. The communication protocols are a bit different between AC and DC, but all the BYD and Neo and Xpeng, all these vehicle manufacturers have these ports. And Tesla has all-in-one sort of charging protocol, and they have only one charging port adapter to use in both scenarios. So moving to the next slide, there we are going to see how the charging station is formed and what are the main operations and functionalities in a electric vehicle charging station. So it is so this is in the picture. You can see our main charging station, which has around 10 or like around 12 charging points like EVSCs. We have fast charging points as well as slow charging points. So normally it is occupied like mostly occupied in morning hours and evening hours. And in the daytime, some of the people who work in that area used to plug their vehicle and do a slow charge, because slow charge actually helps the battery to to stay in a good condition for a long time. So the main functionality or main requirement of a charging station is to regulate the electrical current and make sure that is best possible current for the battery is given to the EV. So the EV will communicate with the charger to requiring this amount of current that I need. So likewise. And also this charging station should have proper insulation and proper electrical connectivity from the grid to the vehicle. So it should have AC and DC residual current detections and MCBs and all the transformers and all equipment that needed to not overload the grid. So when we are placing the charges, we were very conscious about that, because when everyone is using fast charging at some point, there are pretty much of chance that our network cannot handle. So when we're building such charging stations, so those protection circuits needed to be placed. And and all the chargers should detect any latched contacts and relays, because we are delivering, like the chargers are delivering hundreds of amperes to the vehicle. So use in a copper cable. So it generate heat, and all the terminals can be get heat, and they can be welded to the vehicle. So which is a very disastrous situation where the power is drawing constantly and you can't remove the vehicle from the charger. So catastrophic events can happen. Fire can happen, like fire or blast, or that can happen. But it is very much regulated, and uh, it is closely watched by the charger. Uh, so if anything such thing happen, the charger it will direct. There are a lot of redundant ways to close it. So the energy metering should be there. Uh, and also automatic disconnect when the hardware fault is detected. Likewise, I described previously, and the power shut off and some battery damage or anything that happen when the charger should stop. And there are safety lock features to prevent current from flowing when the charger is not connected to EV. So if so, there's a security concern. So someone is so the current should not flow to the charger which is not connected to the EV. And also there are some sort of high-end features that should allow should or that will allow the charging infrastructure operator, which is checking the bay occupancy and like schedule charging. So you can schedule for your vehicle to charge for some time uh, do that, and some live session monitoring. And it is great that if you can see the charging curve of your vehicle real time. So those things are there in with those operators. So from mobile app or something, you can see your charging graph likewise, and various methods to top up as well. Right. So here comes to the main part of this sort of series, sort of this lecture. So let's focus. Let's study on what are the main type of charges at the present. Right. So as I gave you a brief introduction of in previous slides, there are three charging levels: L1, L2, and L3. So the L1 is, as I talked, the previous, it is the home version of the charger. So most L1 chargers comes with the manufacturer, with the vehicle. So it can deliver up to 1 or 2 kilowatt in your home 13 ampere wall sockets. So that is a very slow charger, and it will take around 5 to 7 hours to charge your vehicle. And that is also convenient sometimes when you go home and you can connect your vehicle to your wall socket if you are not going early in the morning the next day. And the other type of charger is the L2 chargers. So they have two separate charging types, two separate connection time, utility connections type, like single phase and three phase. So if your location have three phase, you can go to the three phase option that they will deliver 22 kilowatt to the vehicle. And if you have only one phase, so you can connect it to deliver 7.4 kilowatts. So the maximum current rating that can handle by type 1 and type 2 connectors are 32 amperes. So the connectors, that is a maximum level you can go according to the standards of the connectors. So these standards for L1 and L2 is governed from SAE J1772 and ICE 61851, all these two standards. And L3, on the other hand, is the DC fast charging. So it can handle two voltage levels. Like in the vehicles, they have two sort of architectures, 400-volt architecture and 800-volt architectures. So the charger should handle both the 800-volt and 400-volt architecture, and it should be able to deliver 100 plus amperes. So the power that it can deliver is 50 to 400 kilowatt. So it is 400 kilowatt is like really fast chargers. So that type of chargers fall into L3 category, where governs by the standards SAE J3068 and ICE 61851, the previous standards as well. So those are the main charges in the present, the levels of charging based on the power. And there are other type of charges as well, but it is those type of charges are not very famous in our country and in other countries as well. And the one type is battery swapping. So it is sort of a technology which is it is a type of charger. It is considered as a EV charging technology. That is why I placed it after under this sort of topic, because it is a way of charging as well, a type of charging, where you can park your vehicle into a cabin or something. So it can just switch or swap your batteries within a couple of minutes. So it is remove your batteries and then plug another battery pack to your vehicle, and then you can go. So it is sort of like playing the vehicles, the playing toy cars where we use in our childhood. So it can remove the batteries and plug new batteries and get your vehicle moving. And the other thing is the solar chargers. So you can, it is very famous if it is possible to put on a roof of a car parking station. So you can park your vehicle and you get the shade and also charge your vehicle. But we know that it is very so only very like very the current that can draw from a from EV PV panels is very low, like very less. So so it takes a large time to charge, but it is also available in some countries as well. And the other type of charges is overhead charges. So in a bus station, some places like that, you can park your vehicle and it will connect to a battery in overhead charges. So those charges are not sort of available in our country, and some other countries might have. And the other type of charger is the wireless charging, which is will be on the next couple of years, because there are a lot of researches happening in that area. So it will be popular in the future. So yeah. So let's talk about, let's get a brief understanding about the L2 chargers. So the key functionalities of this L2 charge is to deliver 7 kilowatt to 22 kilowatt charging power. And it is significantly, as I told previously, it is significantly faster than the L1 home charge. because it can only deliver a very low amount of power. And you can like translate 10 to 60 miles a range per hour by charging. And and all the protections should be there. So you can see in the picture, there's a sort of L2 charger. So these chargers should contain all these sort of features. Like it should for in the safety aspect, it should detect all the ground faults, overcurrent, short circuit, and it should also monitor the temperature of the wire and all the circuitry. Because to protect the vehicle and all the users, and and the charger itself. And the communication protocol uh, is the one I previously talked, and it communicate with the EV to get the part of the current requirement of that vehicle. And then it should be able to adjust its current from based on the requirement from the vehicle. So if vehicle require a certain amount of current because uh, it is capable current, so it communicate in the beginning. So that communicated current should be delivered. So I'll tell you how it is communicated to the charger. And then it should have a user authentication and payment schemes that to to uh, to charge for your uh, uh, charging attempt. And then connectors has two type of connectors. So the type 1 is the a single phase connector, and type 2 is the three-phase connector. And it should also has the durability and weather resistance. So and IP classes. So these standards should be there because these chargers are designed to put outside and in a charging location or in a wall mounted in at your home. So these sort of weather resistance should be there. And here is sort of a reference design of such a L2 charger. You can see in the top image, there is a grid, and this is our EVSC, and the third level, it is there, the vehicle is there. So you can see the battery pack. Inside the battery pack, there is a battery management system where that monitors each cell in the battery. Like there are a large amount of cells in the battery, so the BMS detect all the voltages of each and every battery and the temperature as well. So the BMS is one that requires and communicate with the charger to provide the required current, and some in the fast charging, so it provides the uh, charging percentage and the battery temperatures and all those information about the vehicle. So you can see there is a OBC, which is the onboard charger inside the vehicle. So if you are using AC, if you are using L1 and L2, the current will flow through the AC to DC converter and sent to the battery pack. So if you are using a fast charger, it is bypassed, this AC to DC converter bypass, and it is directly connected to the battery pack. So in the bottom diagram, you can see in my left hand side, you can see the three-phase is coming to the charger, and then there is a residual current detector in the as a first element as a first element of the charger. So if there is any leakage current, if there is any DC leakage or AC leakage in the current, the RCD will detect. So those colored boxes should be inside this charger. So so if there is any leakage current, the RCD should detect, and it should communicate. It should send the information to the microcontroller in the charger. So when that happen, when there is something happen, the charging should stop, and then the current flows through the contactor. So the sort of electrical diagram inside a charger, inside L1 and L2 charger, is very simple. because the only requirement of that the only operation of that charger is to turn on and off the connector. But it is not the case, because uh, turning on and off can be easily done, but it is not, uh, because to handle the charging process, you need to have other authentication method, the use authentication, and managing current, and all the operations should be there. And that operation should be done by a microcontroller inside the L2 chargers, L2 chargers. And there is a so you can see in the green box there is isolated power supply and backup supply. Some chargers it has a backup supply and a battery, but some chargers it does not have. And there is a RCD, as I mentioned, and then there's a relay driver that drives the relay based on the input from the microcontroller. And there is another circuitry that need to be there to detect the charger is welded. Uh, so there is a particular sort of uh, circuitry design, standard design to put there and detect if there is any welded circuits. And you can see there is other two boxes like pilot wire and plug lock driver. So the pilot wire is the main sort of communication wire between the L2 charger and the vehicle. So the pilot wire, through the pilot wire, it communicates. It's a required current and the charging state of the vehicle back and forth. So that is the crucial sort of connection to the charger. And the other sort of communication line is the plug lock driver that detects any sort of locking mechanism of the vehicle, and it communicates to the MCU. And all these microcontroller connect to the microprocessor inside the charger. That microprocessor connects to the internet and network to handle user accounts and authentication methods as such. So that is the connection. Normally, the connection happens. So this is a reference design from Texas Instrument, I guess. Yeah, Texas Instruments. So it is available even in the internet. So you can refer more on these standards. So all the charges built in this in our countries, on all the other manufacturers are based on these sort of reference designs, because uh, they are tested, and all their equipments, all uh, their that graded components are they manufactured as well. So yeah. So I will go through briefly of what are the control pilot. Control pilot is a pilot wire I described previously. So it verifies that the vehicle is present and connected. So that wire, so I will show you the waveforms of this control pilot in the next slide. Uh, Before that, so it verifies the vehicle is present and it is connected. So it is understood from the charger. So these key points are the thing that communicate to the uh, charger from the vehicle. So verifies that the connect is present, and then it permits the energization. It permits the current to flow from the charger to vehicle, and then it transmit equipment current rating to the vehicle. It transmit the current that can be delivered by the vehicle, and it monitors the presence of the equipment to the ground. So if there is any ground fault or if there is any leakage from the vehicle, it detects and it sends back to the charger to let the charger know to stop the charging. Um, so that happens actually. We might not think that these protections are required by in ChargeNet. We have exported some of the charges to some other countries like Georgia and India. So there we see almost all the problems with the vehicles where they have leakage current, and where when the temperature is too high with the charger and the battery temperature is too high. All the errors, all the problems, all the issues, all the protections the requirement of all these protections are like they are when we are doing business with other countries and even in our countries as well. So yeah, back to the slides. So the monitor the presence of the equipment and establish a vehicle ventilation requirement. So that is also a good feature. So the user can turn on the AC and a user can stay in the vehicle even when it is getting charged. So that is communicated to the charger. So it to using the pilot wire. And yeah, so and in the dots I have mentioned so how it is communicate with the one wire from the vehicle to the charger. So it is based on some voltage level. It is based on pulse width modulation. So there is the 1 hertz signal, PWM signal, uh, communicate going through between the pilot wire. So it is plus and minus 12 volts. And there is voltage levels that indicates different states of the charger and the vehicle. So if the pilot wire has a voltage level 12, 9, and 6 and 0, that indicate the states. And the PWM signals percentage, it detects the current requirement from the vehicle. So you can see in this slide, the first image shows how to communicate with the, let's go to the figure 2, the control pilot voltage levels. You can see. So if it is 12 volt, it is not connected. If it is 9 volt, the EV is connected and ready to charge. If it is 6 volt, the EV is charging, actively charging. If it is 3 volts, EV is charging and ventilation required. And 0 is the error, and not connected is an unknown error. So these voltage levels indicate that state. So yeah, that. But in the figure 3 table, you can see the duty cycle. So if the duty cycle is like 8.3%, it is requiring 5 amperes from the charger to the vehicle. If it is like 25%, so maybe in that area it is 25%. So it is requiring 50 amperes from the charger, and 50% is 30 amperes. Likewise, you can see 66 and 90 and 96. So it is indicating the requirement of the current requirement from the charger. Right. And the other components are the relay drive and well detect. So EV, I have said that several times because it is a very dangerous event where the well is detected. So if it's charging is several hours, detecting a large currents, that the relays uh, have potential risks of malfunctioning. It can be welded, so that should be detected. And all the residual current should also detected from the charger. So there in the standards, it says that for the AC, if the sensor detects a 30 milliampere residual current, it should stop. For DC, if there is a 6 milliampere leakage, if there is 6 milliampere residual current presence in neutral uh, presence in that wire, there's a residual current, it should detect. Uh, so the baselines and neutral wires, so it is a sort of a fluctuate sensor. So all the 3 bases and neutral wire is going to. So during the normal operation without any fault current, all the sum of the current is 0. So that is we know from our theorems, the sum of the current should always be 0. So the flowing, so if it is not 0, and if it detects 6 milliampere for DC and 30 milliampere, the charging should stop. And during a fault condition, the sum of current is not equal to 0, of course. That detects the AC fault. For detection faults, the oscillating driver current pushed through the fluctuating sensor coil and detects duty cycle shift. Yeah. So I think there are some typos there as well. But the idea is that so it should be able to detect the residual current is present. And the MCU is a microcontroller unit in the charger that should control basically the relay driver, the GPIO for the relay driver. So the main output of the MCU is turning on and off the relay driver. But it should be able to, in real time, it should be able to uh, uh, change the voltage and the current should be measured because it need to calculate the energy as well. And the main one of the other feature it should has is to read the current control pilot voltage levels and duty cycle to detect what are the charging requirement of that cycle of that vehicle. And it need to maintain the charging state as well. So it is basically a big state machine that that going through the states of the charge. The main states of the charge is vehicle is connected and it is authenticated for charge, and it is charging and it is falling to error, and it is back to charging is idle positions. So there are a few main states that is like really in depth, but it may not require in this level. So it should always also communicate with a network controller that the MCU cannot directly can, but sometimes it is cannot. If it is cannot directly communicate to the internet or the network, they need the network controller to control that in higher level, because these chargers should have logs or should have logs to see if there is any issues or if there is any complaint. The operators should go back and see the logs to see where the problem is happens, and then they need to fix it. So they need to communicate with the network controller. And the high clock speed required to timely capture the DC fault detection. Yeah. So it need to sample very quickly of the sensor values close to real-time operating systems. Like no, it is close like real-time operations, because it need to detect if there is any IC fault. And then the ADC must have an effective resolution, like small enough to uh, see any difference between a fault and not fault. And then on top of MCU should connect to some, like it is a system on module, so it is sort of a microprocessor that connects to the network. And there is a charging standards as well. To connect to the network, authorized user charger can connect the charger to the network. There is a standards called OCCP, Open Charging Point Protocol. So that using that protocol, the charger should communicate with servers and all the backend to do all the process. And it also handling sort of a display if there is any display, or showing the parameters to the user. The display handling function is also can be done from a microprocessor. And also it is a resource monitor and there's a data logger. And also it should be able to over the air update the firmware of the MCU. So these functionalities should be there in the microprocessor, which is connected to the charger. So here in this diagram, you can see. So in the reference diagram, they use M62 board for their design. So let's go into the other type of charging. So this is sort of DC fast charging. So if the whole idea or the whole environment is changed from AC to DC. So the design is not that simple as L1 and L2. It is not simple of turning on and off a relay to deliver charge. So it should be able to like provide a high power output, like 50 kilowatt to 350 kilowatt. So these other type of chargers only can deliver 22 kilowatt max in L1 and L2. But here in the L3 chargers, which is DC fast chargers, should be able to deliver that amount of power to the vehicle. So that vehicle can be charged like 20 to 30 minutes from 10 percentage to 80. And the communication protocols are there. So those communication protocols have developed by the vehicle manufacturers, uh, CHAdeMO, CC, and Tesla and Supercharger. So the charger should be able to handle these type of uh, communication protocols. And also there should be a proper cooling system because there are power modules inside these chargers that need some cooling because it consumes much energy. It drawing energy, it convert rapidly from AC to DC and deliver 100 amperes of power to the output to the user. So it should have proper cooling systems. So most of the time, these chargers have two sort of ports. So sometimes they can work simultaneously, and some type of chargers they cannot work simultaneously. They can so the one vehicle can charge from a fast charger, and there are other type of chargers as well. So simultaneously they can charge two vehicles at a single time. And there is a UI and display that provide information, real-time information of the charging, like charging status, power output, and remaining balance, remaining charging times. And if there is any error messages popped up, it should display in the screens. And connectivity and smart features. So that is about connecting, like seeing the bay occupancy and some visualizations as well, and connecting to the internet and connecting to the backend servers, back and forth. So user can remote control the charging operations. So there should also be very thoroughly assessed safety features because this can easily can have a shock because the power output is very high, and the durability and the weather resistance should be also be there when dealing with these outside scenarios. So here I'm not going to go through all the sort of DC charging connector standards. So this is the one of the famous standard. So you can see this type of CHAdeMO connectors in Nissan Leafs and also in Porsche Taycan, which is one of the latest electric vehicles. So these standards you can see there are so in the previous L2 and L3 there is only only one or two communication lines. So here you can see there are these 5 and 6 is the main power connector, and all other connectors communicate with the vehicle, with the charger. So so if you can see so this networks, all the circuit is fully connected when the vehicle is properly connected to the charger. So so this is sort of a circuitry which is connected, which is one part is on the vehicle and the other part is on the charger. So when it is properly connected only, uh, these things actually works. So in the top sort of figure shows the main power supply. So there's a main power supply coming from the charger. So power should not go back to the charger. So there will be sort of a diode control mode. And in the future, there is some vehicle to grid architectures will be there. So the charging battery, the vehicle can deliver it is excess power to the grid. So yeah, so it is in the future technologies. So in the power lines connect to the vehicle directly to the battery, and the EV contactor of the in the vehicle can turn on and off. And then there is some other communication line 1 and 10. You can see the circuit will be fully connected when the vehicle is connected, right? So it gives some states of the charger. Charger starts and stops, and there is other connections to be made for the connection check likewise. So charging enable and disable comes from the fourth connector. So all these parameters and all the readings should be like read by the MCU and take necessary actions. And while the charging is happening, the CAN communication is formed. You can see the 8 and 9 wires for the CAN communication. So all the charging states and charging percentage, SOC, and all the things will be communicated through the CAN bus. So this is a brief, very high-level diagram of a DC fast charger. Mm, in the figure 1, if you focus to the first figure, so you can see the AC main 3-phase supply is there, and there are several stages to convert the AC to DC. There should be a converter, and then like there can be few AC to DC. There can be few bulks of these like blue boxes. So in a charger, based on the power which is rated of the charger, so there can be few bulks of these blue boxes. Couple of AC/DC converters, couple of DC/AC converters, and rectifiers as well. So yeah. So this is the vehicle, and this is the battery, and this is a BMS. So the EV charging controller always communicating with BMS directly via the CAN bus. And then these levels convert the AC to DC, and change its current and voltage based on uh, the durability of the battery and the requirement. And in the bigger image, in the figure 3, I'm showing the entity relationship diagram of a power module. So this can be sort of a power module. So it is bit sort of a complex. So it is showing that there is a current and voltage sensing should be there, and always there should be AC to DC conversions, and it should always monitor the temperature of the modules, and there are cooling fans in the modules. Likewise, it is a bit complex, and it should always communicate with the MCU of its states, and those sort of power modules can combine and make a one single charger with a given power. So uh, like so 3 or 4 power modules can be there. So there are certain manufacturers who manufacture those power modules, and even like in our ChargeNet, we develop our own power modules as well. So we use time to then and testing with all these power modules. So the final outcome of this having these power modules is to deliver uh, uh, like regulated current and voltage to the supply. So this charging methods, like in the figure 2, I have shown the continuous current and continuous voltage charging method. So it is sort of concerning about the durability of the charger. So first, from the starting of the charge up to 80% of the battery, it deliver a constant current to the vehicle, and the voltage is increasing, uh, and constant current is supplying until the charging get 80%, and then the voltage will remain same, and then we reduce the current until the current becomes 0, and the charger then the vehicle is fully charged. So from that is a sort of a charging method that safeguard the battery and also optimizing the time of charge. So uh, constant current will be delivered for some time, and then when the battery voltage is up to a certain level, then the current is varying. Current is reducing one by one, and so when it is becomes zero, the charge it requires zero current from the charger when it charged to 100%. So then I'm moving to sort of ultra fast charging. So it is not that popular. So, but it uh, uh, it uh, it sort of clear out the range anxiety that you can see in this sort of cartoon, because when even in fast charging, you have to wait until uh, like few minutes, at least an hour. But in a gasoline vehicle, in a fuel vehicle, you don't have to wait at least like even for 5 minutes to bring your fuel tank from zero to full, right? So it is, so you don't plan for charging locations where you go on a trip or go on an important sort of visit. So, but all the right now, all the people who has electric vehicles should map out all the charging locations to go from a long journey. So they need to plan where they're going to charge. They need to plan how much time they need to spend in a charging location. And the worst case is when there is at their planned location, when the charge, if the charger is not available due to some fault or something like that. So they are in a really bad situation. So you, with the ultra fast charging, the anxiety is supposed to go out. So you can see the AC charging take like 4 or 8 hours, and DC fast charging take like 1 hour to charge from like 10 to 60%. And the DC ultra fast charging, which can deliver more than 150 kilowatt, so it can be charged in just like 15 to 30 minutes. So if it is like 400 kilowatt charger, which is exist in other countries, uh, so there are 400 watt chargers, kilowatt chargers. So they can deliver, like if the vehicle can uh, handle that power, they can charge a vehicle in 10 to 15 minutes very easily. Not very easily, but they can charge. So, so the solution to this range anxiety is building ultra-fast charging stations. And in the second figure, you can see this the diagram, sort of architecture of such station. You can see the main grid is there, and there will be AC bus where three-phase chargers are connected, like three-phase and single-phase chargers connected, like L2 and L1 chargers. And then there will be a rectifier, and then there will be DC bus. And so for to that DC bus, all the chargers shall be connected. So most of these like charging stations that has ultra fast charging should have sort of these sort of big grids, AC buses and DC buses uh, that can handle the charging station as well. Because if some vehicle requires an ultra fast charging, it needed a very high power to that particular vehicle. So at that time, there can be problems of charging other vehicles because the demand to that particular charge is high. So to control that, there should be a way to handle uh, this situation as a considering as a station. So this is sort of the ultra fast charger that has a power rated power supply of 200 kilowatt from Delta Electronics in Netherlands, UFC 200. So I have gone through their specification uh, to uh, to make you understand. So what is it capable of? So it has sort of three phase L1, L2, and neutral and earthing, and it can support 400 volts and 800-volt architectures both, and it can deliver a maximum of 380 amperes at its full charge. So in that case, you can see the large amount of current is delivered to the vehicle through the cable. So the cables should be there are water cooled cables as well. So if you use water cooled cables, the cable inside there is a water loop which cools down the wire, the cable from the charger to the EV. So those things is there present in this in this ultra fast charger. And there is as same as the overprotection and all these GFI short circuit protection underbolt, and there will be more protections in the charger. And in the mechanical, there will be as I mentioned, uh, forced air and liquid cooling power modules and cables should be there. And this power can be regulated, should be regulated as per the requirement. And these are the regulations it complies of: EMC, charging point standards, e-safety standards, likewise. And it supports dynamic power management and controller buttons and display and RFID and NFC, and it also complies with OCCP, the Open Charging Point Protocol. So this is sort of a specification of that particular charger, which can claim as a ultra fast charger. So the challenges of ultra fast charging is that the energy storage system needed to minimize the impact on the grid due to an instantaneous power drawing. So that means these sort of power stations should have a backup power generators, because when there is a large power draw from the grid, so there will be voltage drops in the grid. So to minimize that, there should be a way to give back that energy to the grid for that particular short period of time. And there's other problem of heat generation in cables and power modules. In the both cables and the power modules, it generates a large amount of heat. So there will be a water cooling system or some high level cooling system uh, to uh, to reduce that heat, so that make the charger more efficient. Um, so then there is the investment for these sort of chargers is high uh, for the infrastructure and the transformers and cooling systems and high capacity cables. So these problems are there. For the vehicle side, there are certain challenges as well. Increase the current during the CC stage. There will be increased currents, and that current definitely like harm the battery life as well. The high currents reduce the battery life, so causes permanent damage. So charging a vehicle in like 10 or 15 minutes is fascinating, but again, it damage the battery. Uh, so, and also the higher currents lead higher losses heat. So due to the internal resistance of battery cell and cables. And like the vehicle should compatible enough to plug for ultra fast chargers. And then I'll in the last part of this session, so I'll be going through some uh, 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 of the wireless charging, and you can see so that the wireless charging history comes from the Nicholas Tesla. So he's the one who sort of came up with the idea that the electricity can be transmitted through wirelessly. So he and Edison were in the power war, and in like 90s, and he claimed that the power can be delivered to everyone in the world wirelessly. So he demonstrated that not he demonstrated he demonstrated that concept, uh, which is using Warden Cliff Tower sort of arrangement. He was claiming that they can send uh, electromagnetic signals so that he can deliver uh, uh, wireless power to some to very to other devices. So in the first image, you can see the Nicholas Tesla is holding a bulb. So in the other side of that curtain, there is a sort of a transformer arrangement that uh, generate electromagnetic signals, and the coil in that sort of a bulb gets that power from the varying flux. It get that power, and the bulb light up. So in the figure 2, you can see that Wardenclyffe Tower, where he decided to do that experiment, but he was not successful at that time. Uh, because from the fundamental concern, because he was thinking that if the water can, so his argument was to send these signals through the ground, but at the time it was a concept, but it is not feasible. Later on, people uh, conclude on that as well, and and for the wireless charging systems for the electric vehicles is not my like this. It is not sort of imagination things like that, because the Society of Automotive Engineers published a sort of official standards uh, for wireless charging in 2020, and there are a lot of researchers happening around the world to make a charger, make a vehicle that can charge uh, using wireless charging. And in 2023, Tesla acquired a German wireless EV charging supplier. So it is very prominent that the Tesla will focus on that area uh, as well. So the wireless in the figure 3, you can see wireless power transmission, how it is be done. So the charging station will be there, and there will be a transmission coil and the receiving coil in the both side. In the ground, there will be a transmission coil which generate a varying magnetic flux, and the receiving coil will receive that power. So you don't have to have sort of a vehicle built for wireless communication, wireless power transfer. You can plug that receiving coil to a vehicle and connect it to the battery and to your onboard charger. So that is possible. But as for like challenges, like there are, if somebody is building up that sort of wireless charger, so they have to consider about uh, the interoperability as well, because every vehicle should be able to get the power from that, and the electromagnetic capability, how it handles, and what are the damages, EMF, what are damages it can do to the other electronics part of the vehicle. And there should be a minimum performance as well. And the distance from the charger to the vehicle should be uh, in a considerable range. And those things are there. So let's see very briefly about this inductive power transfer. So it is basically the electromagnetic induction, as you might already know. So the Maxwell equations claim that if there is a very fine electric field, there will be inside a coil, there will be a varying magnetic field. So if we send AC source, like not AC in that sense, high frequency uh, the voltage to the coil. So it can generate a magnetic field which is varying. So that varying magnetic field uh, can be captured from another coil, that from the receiver side, and from the Faraday's law, this varying magnetic field can generate an EMF, and that EMF will be then rectified and sent to the battery of the vehicle. And there is a resonant circuit, that is called resonant inductive coupling. So there we place resonant capacitors to the in both the coils. So it forms a sort of LC circuit that has a resonant particular frequency. So by tweaking that frequency, the distance between these sort of coils can be varied. So this is in the photo, the first figure. So is a Tesla 50-watt wireless charger for it is not for the electric vehicles, but for the components and some sort of a like charging pad of your mobile phone. So to charge electronic equipment. So inside this setup, it is comes with uh, coils using the same principle. So this is a Tesla made 50-watt wireless charger for the electronic items, not for the vehicles. But sooner or later, they will make their first wireless charging capability as well. So this is like some basic sort of circuitry. So first stage will be a high frequency inverter that convert the DC power input to a AC high frequency uh, supply. And then it goes to a transmission coil and the resonant capacitors are there. And so the transmitter coil will transmit the energy as a varying magnetic flux. And that will be received by the receiver coil, and there will be also resonant capacitors. And from that state, there will be a rectifier to convert the AC current to DC. And there will be filter circuits. And finally, the DC out should be sent to the load, which is the battery. So this is sort of a comparison between the transformer theory and wireless charging, because it are in the same domain, because it's in a transformer, it does the same thing. It generates electricity, and it generates a very magnetic flux, and the secondary coil get the current. So there is a power transmission between primary and the secondary coil. For the wireless charging, it is all the same. So there will be a charging pad, the transmitter coil, and there will be a receiving pad. But the most importantly, the thing is in the transformers, there is a laminated iron or ferrite core that make this the magnetic flux flow through easily, effortlessly between primary and the secondary core. But the wireless charging, it is not possible. So because of that, it is still in the research and development area, where because when you like increase the distance between the coils, the efficiency will grow in significant amounts, and it won't receive that much of energy, because it does not have such laminated or iron ferrite core like a transformer. So the wireless charging is having that sort of problems, and if you compare transformer theory to wireless charging, but I've read some in 2014, some have claimed that uh, they have like they have achieved like 90% efficiency from a wireless charging. I have read some papers, but so it is still in the R&D domain. So yeah, again, this is sort of the challenges that EV charging is inductive power transfer. The first is a magnetic loss due to air gap, and the alignment sensitivity, the misalignment with the transmitter and the receiver coil. So this alignment problem as well, again, because it should be properly aligned with all these flux. Otherwise, most of the power will get lost, and there will be that problems. And different ground clearance of the vehicle. So the vehicle to vehicle, the ground clearance is vary because of the tire pressure, and even with the weight, the ground clearance will be changed. And the heat generation will also be there. So it will be heated, because there will be the currents happen in the other metal parts of the vehicles, the vehicle. And then the cost of the equipment and infrastructure and the electromagnetic interferences will be there. And also it is not publicly accepted right now, because it is not available. But in the future, it is possible. All right, so I think we have come to the end of these sort of slides, and so yeah, so we discussed we did not spend much time on the latter part of this discussion, but you also need to have the basic understanding of what is the current nature of the charging infrastructure before innovating it. And also, I think hope you got a good understanding about how these power levels of the electric vehicle charges. And I think you have good understanding of L1, what are L1, L2, and L3 charges are. So why it is uh, have different types as the power levels, and then you have a basic understanding of their electronic circuitry, and what are the safety concerns, what are the standards, likewise. Uh, yeah, so I think you might have a good understanding about overall understanding about charging point stations and how it operates. Yeah, so thank you. So this is another cartoon, so I put it there. So yeah, so I think it is self-explanatory. So thank you for listening and staying with the discussion to the end.
Thank you, Mr. Kasun, for that informative session. I believe that your insights have truly added depth to our participants' understanding of charging infrastructure innovations, and your ability to simplify complex concepts is commendable. I believe the foundation that you have laid today will surely help our participants in their academic and professional journey. So as we move forward, we'd like to open the floor for a Q&A session. We invite you to raise any questions or doubts you may have about the content that was discussed today. I encourage all the participants to make the maximum out of this opportunity and ask questions and clarify doubts. To ensure that we have enough time to address as many questions as possible, we kindly ask you to keep your questions direct and to the point. You may raise your hand and I will call out your name. Then you may unmute and direct your questions about the keynote speech to Mr. Kasun. Or you may use the Zoom chat to ask your questions and I will read it out to our speaker. Yeah, encourage you all to take this opportunity and raise your questions to our speaker. While we encourage everyone to take this opportunity to engage and seek clarifications on any topics discussed, we understand that our participants may require more time to gather their thoughts. But time is of value. So we will head on with the program. However, if any problems do arise, please reach out to Y2NPro team and we will do our best to get them answered. Moving on, we would like to take a moment to express our gratitude to our esteemed speaker, Mr. Kasun Jayalath, for accepting our invitation and sharing his valuable knowledge and expertise with us. Please accept our token of appreciation, sir.
Thank you.
Thank you once again, sir. Before proceeding, let's take a group photo to remember this valuable time we spent together learning today. I kindly request the audience and the Aussie members to switch on your cameras to take a group photo. Please make sure to use the virtual background we have sent you in the meeting invitation. Let's wait another few seconds till everyone is ready. Come on, guys, let's switch on your cameras. Okay, I think we are good to go. All right, everyone, get ready. On the count of three, I'll give you a cue to smile and pose. Yeah. Let's wait a bit more time. Yeah, I hope everyone is ready now. 1, 2, 3. Say cheese. Let's make sure we capture a good shot. Are we good to go, Dushinta?
Yes, we can go ahead.
Yeah, thank you all. Also, please note that the quiz will be conducted on 5th of October at the end of the workshop series. We have shared a feedback form in the Zoom chat now. Also, you can scan the QR code on the screen to access the feedback form. We kindly request you to take a few minutes to fill it out. Your feedback is extremely important to us as it helps us to continuously improve and provide you with better experiences in the future. This will also be considered for your attendance. Moving on, the next session will be held tomorrow, the 25th of August from 6 p.m. onwards, where Dr. Bishant Kulapela, the CEO of Cyrus EV Chargers, will join us to take you through further charging infrastructure innovations. As we near the end of the session, we sincerely hope that you found the workshop informative and thought-provoking, and that you leave with new insights and ideas. And with that, we conclude today's workshop. Thank you once again and have a good night.